All right, here's a couple of proof type exercises. So we want to show that the definite integral from a to b of f of negative x dx is equal to the definite integral from negative b to negative a of f of x dx. And then if we can, let's try to use this thing, once we've established that it's true, let's use this fact to prove this fact. And one that should be okay using geometric intuition. So, prove that if f is an odd function, in other words, f of negative x is equal to negative f of x, so like the sine function is odd, y equals x cubed is odd, y equals x to the fifth, so on and so forth. So prove that if the function is odd, then the integral from negative a to a of f of x dx is equal to 0. Here's a picture of a typical odd function. Remember, odd means origin symmetry. So if you go from negative a to positive a, there is as much area above the x-axis as there is area below the x-axis. So remember, the definite integral is assigned area, and so these two things will cancel each other out. That's why you would get 0. But we want to use u substitution to prove that rigorously, and prove it rigorously without using limits of Riemann sums. All right, let's prove that the integral from a to b of f of negative x dx is equal to the integral from negative b to negative a of f of x dx. And so we want to do this using u substitution, and we don't want to have to use a limit of Riemann sums. So I'm just going to let u equal to negative x. And then I'm going to run the usual differential program. So now that means du is equal to negative dx. And so that means that negative du is equal to dx. And so now on the left-hand side here, this integral is going to become, change the limits of integration. So u of a is equal to negative a, and u of b is equal to negative b, just like we've always done. And so now, the integral on the left-hand side, so the left-hand side is equal to the integral negative a to negative b f of u and dx, that's negative du. And so now I can write the negative sign out front, and that's going to switch the limits of integration. So now this is the integral from negative b to negative a, f of u, and then the negative sign switch the limits of integration. So we just get f of u du. And now, remember, u is just a dummy variable. So I can just as easily swap out whatever variable I want. F of t dt, f of x dx, so that's what the problem asks us to show. So I'm just going to write the integral from negative b to negative a f of x dx. And so that'll do it, right? So we started with the left-hand side, we worked our way over and got the right-hand side just using the regular old u substitution program. So we want to prove item 2, that is, if f of x is an odd function, then the integral from negative a to a of f of x dx is just 0. So now, here's what we proved on the last board, that the integral of f a negative a thing, d the thing, from a to b is equal to the integral from negative b to negative a, drop the negative sign, so f of x dx. So we're going to use this fact in our proof here. So now, I'm just going to start with this integral over on the left-hand side and just try to apply u substitution and see what I get. So let me call this thing on the left-hand side, I'll call it I. So capital I is equal to the integral from negative a to a f of x dx. Now, you can write x as negative x. That's all I did from here to here. Write x as negative x. And so now I've got the integral from negative a to a, f of negative a thing, dx. And so now, what does this say? It says I can switch the limits of integration and make them negative. So negative a goes up top, negative a goes to the bottom, and now I can remove the negative sign when I do that. So I'm applying this thing from here to here when I go from here to here. So make sure that you can see that. And so now I got the integral from negative a to positive a, and then using the fact that f is an odd function, I can write the negative sign out in front. So that's how I got from here to here. And now I can write the negative sign in front of the function out in front of the integral. That's all I did from here to here. And so look, we got negative the thing that we started with. So that's negative I. So we've shown that I is equal to negative I. But remember, I is a real number. And so the only time a thing is equal to its own negative means the thing had to have been 0 in the first place. So for example, you can add I to both sides, you get 2I equals 0, divide by 2, that tells you that I is equal to 0. So now we know that this integral, right, this integral that we call I must be equal to 0.